The temperatures we use here in the lab are genuinely the coldest temperatures known to man. The Celsius scale is geared to human sensation. So when water freezes, we say it's 0 degrees, and when it boils, it's 100. And we live in the world somewhere in between. But that's not a physical definition of temperature. The physical definition of temperature is linked to particle movement. The faster a particle moves, the hotter it is. If you take this as your bottom line, then there really is an actual defined 0 point when the particles stop moving altogether. That's what we're trying to achieve.
Michael Köhl is one of the world's leading researchers in experimental atomic physics and quantum optics. One of the things he investigates at the University of Cambridge is the behavior of ultra-cold atomic gases. Experiments of this kind can model dynamic phenomena in atomic particles, making it easier to study their behavior.
We try to reduce speed so that phenomena become observable, especially dynamic phenomena, such as how matter and spins are transported, because this is relevant for all kinds of transport processes in solid-state physics, in information transfer. We constantly want to transfer information from A to B, so we have to know how the transport works.
These experiments are designed to extend fundamental knowledge about physics, but they can also be used to develop superconductors for use in medical technology, for example, or have a decisive impact on the advancement of quantum computers. The experiments are dependent on laser beams of differing intensity and are therefore sealed off. The goal of the sensitive and cost-intensive test setups is firstly to fix ultra-cold atoms and ions, and then to manipulate them with optical tools in order to study their physical behavior.
One direction we are particularly interested in is trying to understand how systems composed of multiple particles behave. These are model systems for solid-state bodies, and there are a lot of processes in solid-state bodies that we don't yet understand. Superconducting is one of the phenomena that we're not sure about how they work, but which are extremely relevant technically, and we're now trying to reconstruct them in a gas so that we can understand the mechanisms better.
The gas serves as a representative assembly of atoms in specific states, whose behavior can be observed more precisely in experiments like these. These systems can now be investigated around the globe and have generated enormous interest both amongst practitioners and theoreticians. This test setup, for instance, is supposed to elucidate how an ultra-cold atom, which has been excited by a laser beam in an ion trap, emits energy. The findings of such work could be of major benefit to the transmission of quantum information over great distances. Pioneering experiments, even for Cambridge, that open up new paths in atomic physics and quantum optics.
They didn't have our area at Cambridge at the time. For such a famous university, it was something of a lacuna, and they wanted to fill it. I saw this as a tremendous challenge to establish a completely new area at such a prestigious university.
The next big challenge is waiting for Michael Köhl and his team in Bonn. He is set to lay the foundation stone for a center of excellence at the intersection of quantum optics and condensed matter at the University Department of Physics. Bonn will attract the attention of physicists from all over the world. New arrivals of this caliber are always a magnet for attracting other scientists who are enthusiastic about their research. Mr. Köhl is a very dedicated, expert colleague who I'm sure will do a great deal to promote physics here in Bonn. We are very pleased that he has decided to join us. At present, Köhl and his team are in the middle of preparations for the move. This is not only an enormous step for his staff, but also a fresh opportunity to set up new experiments. Some of the test setups will be dismantled in Cambridge and meticulously reassembled in Bonn. Other experiments will use completely new designs.
The challenge is to get everything running at the same time in such a complex experiment. We have electronics, we have optics, we have computer control systems, we have vacuums. These are all building blocks we have to put together ourselves, and then they all have to work together at exactly the same moment.
In Bonn, Michael Köhl and his colleagues will work on new model systems that are in demand in many fields of research. The production of ultra-cold temperatures is always the major focus. Currently, the record inside the shiny silver magneto-optical traps is 200 nanokelvin, just a millionth of a degree above absolute zero.
In the future, we hope to be able to reduce this by a factor of 10. That will open up a whole array of new phenomena for us to study and understand. And we would be breaking into regions which haven't even been mapped in theory so far.